Hello everyone. In this video we're going to learn some new factoring techniques that require some special factoring formulas in order for us to be able to handle them. We've already seen factoring out the greatest common factor, and we've also handled different types of trinomial factoring. So now we'll move on to a few methods that have not been covered yet. While it's true that factoring out the GCF and trinomial factoring are two of the most common types of factoring we may encounter, there are other types of factoring we need to master for a complete repertoire when it comes to factoring. And we'll start with a very important variant that will come up very frequently as well, called the difference of squares. The first formula is one that should be familiar with us, because when we were doing polynomial multiplications and we multiplied two conjugates, which are basically two expressions that happen to be the sum and difference of the same two terms, then we ended up with f squared minus l squared. So we've seen this formula going from right to left before. So now we're just going to be using it in this direction. So, of course, seeing that it's true is very simple. We can just multiply f plus l by f minus l. Here we get f squared minus fl plus fl and minus l squared. These will, of course, cancel out. They're like terms, and we're left with just f squared minus l squared. All right, so here we're going to factor this problem. As always, we'll always look for a GCF first, and if it happens to be anything other than 1, we're going to factor it out. We notice here the GCF is indeed 1, so we proceed. So we do notice that here we do have a difference of two perfect squares. So the formula we're going to be using is, of course, f squared minus l squared equals f plus l times f minus l. You may, of course, see this formula with f minus l written first, followed by f plus l. Makes no difference. They're exactly the same because of multiplicative commutativity. So we're going to be applying this formula. It's helpful to see what is this first expression a perfect square of. And of course, that would be 3x, and the second term here, 16, is a perfect square of 4, so like so. So now we can see the role of f is being played here by 3x, and the role of l is being played by 4. So now we're just going to apply this formula with 3x used instead of f and 4 used instead of l. So we end up with 3x plus 4 times 3x minus 4. And that's as simple as these are. And anytime you have time on your hands, you can, of course, check. It's always recommended. So here's another one. You should definitely pause the video and try this on your own first before you come back to join the video. All right, so if you notice, the GCF here is again 1, so we can proceed. Now we notice 25 is a perfect square, u squared is, of course, a perfect square, 81 is a perfect square, and so is v squared. So we do have a difference of two perfect squares. It's helpful to write down what those expressions are whose perfect squares happen to be these two terms. And of course, what we need to square to get 25u squared is 5u, and what we need to square to get 81v squared is 9v. So to apply the formula, f squared minus l squared equals quantity f plus l times quantity f minus l. We are going to use 5u to play the role of f, and the role of L is being played by 9v. So we're simply going to get f plus L, so 5u plus 9v times f minus L, which is 5u minus 9v. If this appears much simpler than trinomial factoring, is because it is. So we do notice in this next problem we do have a difference of squares as well. The coefficients are not whole numbers or integers, but they are perfect square rational numbers. So we go ahead and use 1 for the GCF, but as far as the expressions, we need to square to get those two perfect squares. Of course, we can square 1/10 x to get 1 over 100x squared, and 1 over 11y to get 1 over 121y squared. So the role of f here is being played by 1/10x, and the role of L is being played by 1/11y. So when we go ahead and write the formula, f squared minus L squared equals f plus L times f minus L, we can go ahead and use 1/10 x instead of f plus 1/11 y instead of L. And of course, now we just need the difference of those same two terms. So 1/10 x minus 1/11 y. And that completes our factorization for this problem. In this problem, we can see that the GCF is 1. We go ahead and factor. We do notice that x to the 4 is a perfect square, and so is 16. We know that x to the 4 is a square of x squared. So we can write this problem like this, and we know that 16 is a square of 4. So for this round of factoring, f is x squared and L is 4. So according to the formula, which is f squared minus L squared equals f plus L times f minus L, this is going to factor as f plus L, so x squared plus 4 times x squared minus 4. Now notice that we have no formula for a sum of squares. Most significantly, you have to be aware of the fact that a squared plus b squared is not a plus b squared. It's one of the most common errors in mathematics, right? So what do we do with the sum of squares? There's not a whole lot we can do. Sometimes, for example, if you have, say, 4x squared plus 16, you can factor out a GCF to get this, and then that's about all you can do. So there is not a technique for factoring sums of squares, at least not in intermediate algebra. Once you get to college algebra, we'll discover some ways of factoring those, but that's going to require sets that are beyond the set of real numbers. We will study that a particular set which goes beyond the set of real numbers by the end of this term. It's called the set of complex numbers. Okay, so as far as we are concerned, we leave this one alone. This part is not factorable any further. But we notice here, we even though we did one round of factoring, that we have still a difference of squares here that we can be factored again. So we leave the x squared plus 4 alone, and we zoom in on this part and realize, hey, we can use f equals x and L equals 2. So we end up with x plus 2 times x minus 2. Now we have completely factored this problem. A lot of times students stop at this point, which is problematic because Remember, we always factor completely. All right, so we're going to try to factor this. Of course, 20 is not a perfect square, nor is 125. X to the 6 is, it's a perfect square of x cubed, so is x to the 4, but these parts aren't, so that's not good enough. But we notice that there is a GCF here that we can factor, so let's try that. The GCF is not 1 here. It is in fact 5x to the 4, right? For 20 and 125, the greatest common factor is 5. For x to the 6 and x to the 4, it's x to the 4. So we have 5x to the 4 as the GCF, which we will go ahead and factor out. And that leaves us 4x squared minus 25, and that's it, just 25. So after we did the factoring out of the GCF, we notice we do have a difference of squares. We can always write that as the square of 2x minus the square of 5. So we end up with 5x to the 4 times 2x plus 5 times 2x minus 5, like so. All right, and we go ahead and wrap it up for that problem. So just always remember, take out the GCF if it's anything other than 1. So the other special factoring formulas that are useful, nowhere as essential as the previous one, because with the previous one, if you don't know it, you just won't be able to factor it, but also time saving, especially later when we want to do this method called completing the square. We're really going to have to be good at recognizing these, so that's why we'll cover it. So first of all, again, we've seen both of these formulas going from right to left when we handled the set called special products after when we were multiplying polynomials before in a previous video. So we noticed that f plus l quantity f plus l squared is just going to be f squared plus 2fl plus l squared. Very easy to verify here. Just multiply f plus l by itself and you get f squared plus fl plus fl plus l squared. These combine because they're like terms, so we get f squared plus 2fl plus l squared. And same goes here for the square of f minus l. We notice that if we multiply it out, we just get f squared minus 2fl this time plus l squared. Now we're going to apply these to try to factor certain perfect square trinomials quickly. These two expressions are what we call perfect square trinomials, the ones on the left, because this one is the perfect square of this binomial and this one is the perfect square of this binomial. That's why they're called perfect square trinomials. It's a trinomial that happens to be the perfect square of a binomial. Okay, so the telltale signs of having a perfect square trinomial is, at the very least, you want to look for a perfect square in the first position and one in the last position. We have that here. But that is not enough, because remember, we have f squared plus 2fl plus l squared equals quantity f plus l squared. So there's always that middle term we need to make sure works out as well. In other words, if we determine what f and l are, we have to make sure the middle term is 2fl. So in this problem, the proposed f is x, and the candidate for l is 7. So if we choose those as f and l, then we calculate 2fl, and we get 2 times x times 7, which happens to be 14x. So we verified that this trinomial is indeed a perfect square trinomial. So it's a perfect square of this binomial. So here we're going to have, instead of f plus L, we're going to use x plus 7. So this trinomial is in fact the square of x plus 7, and it is a perfect square trinomial. The GCF was, of course, 1. You have to be extremely careful not to solely rely on the first term and the last term being perfect squares. Here again, the GCF is 1. So our proposed f is once again x, and the proposed L is 7. But if we try to satisfy the formula f squared plus 2fl plus L squared equals quantity f plus L squared, we want to make sure that middle term happens to be 2fl. But with that f and that L, 2fl will be 2 times x times 7, as we just saw in the previous problem, which is 14x. But this causes a problem because that is not 14x. So we conclude this is not x plus 7 squared. So just because you have a perfect square in the first position and in the last position, that does not mean the trinomial is a perfect square trinomial. Be careful with that. How about this problem? Try it before you come to watch the rest. Alright, so I hope you did realize we have a GCF that's non-1, meaning something other than 1. And what is it here? Notice, for 18, 24, and 8, the GCF is 2. For u to the 7, u to the 6, and u to the 5, the GCF is u to the 5. So if we factor out the GCF 2u to the 5, that leaves us 9u squared minus 12u plus 4. So now we have a trinomial, and it looks like the first term of that trinomial is a perfect square and the last term is. Since the middle term is minus, we know this is going to be of the f squared minus 2fl plus L squared variety, which gives us f minus L squared. So the candidate for f in this case is going to be what you need to square to get 9u squared. And of course, what we need to square to get 9u squared is 3u. You understand that? Notice, if you take 3u and square it, what do you get? You get 3 squared u squared. What's 3 squared? 9. So, and the candidate for L is 2. So the middle term better be negative 2fl. So that's negative 2 times 3u times 2, which is negative 12u, which happens to be what we have. So this is indeed a perfect square trinomial, and we can write it as f minus L, quantity f minus L squared, where f is 3u and L is 2. So we write it as 3u minus 2 squared. And of course, notice that we carried the 2u to the 5 as we should. Whenever we have a GCF like that, it's going to be part of our final factorization. All right, make sure you can handle that before we proceed. All right, so the last two special factoring formulas we're going to study have to do with cubes. Now, if you recall, we had no formula for a sum of squares, but we do have one for a sum of cubes, and it's right there. So we get quantity f plus L times quantity f squared minus fl plus L squared. That's the factorization of f cubed plus L cubed. For f cubed minus L cubed, we get something similar, but the signs are different. We get quantity f minus L times quantity f squared plus fl plus L squared. Notice that when we're dealing with the sum, the signs that we see in the formula kind of alternate. The first one is a plus, the second one we see here is a minus, next one is a plus. When we're dealing with a subtraction, f cubed minus l cubed, the sign between the first two terms in the first parentheses is group of parentheses is minus. The ones in that second parentheses group are all positive. Kind of some of the ways you can use to remember those. Now the verification again is simple. Just multiply f plus l by f squared minus fl plus l squared in a table. So f times f squared is f cubed. Here we get minus f squared l. Here you get plus f l squared. For this one we get plus f squared l. Here we get minus fl squared. For the last one we get plus l cubed. So notice the fact that the two terms in blue are like terms and opposites, so they cancel out. The two terms in red are like terms and opposite as well, so they cancel out too. Then you're left with f cubed plus l cubed. Okay, same here. We multiply f minus l by f squared plus fl plus l squared, so we get f cubed plus f squared l plus fl squared minus f squared l minus fl squared minus l cubed. Again, the terms in blue are like terms and opposites, as are the terms in red, so, or maroon, whatever that looks like to you. So we also end up with f cubed minus l cubed as we stated here. So those are the two formulas we're going to use now to do some factoring that we weren't able to do before. So just as in the case of all other factoring problems we've done, we'll look for a GCF first. We notice here it is 1. So we proceed. It looks like we have a sum of cubes here, so we need to recall that formula. F cubed plus L cubed equals quantity F plus L times quantity F squared minus FL plus L squared. And of course, what's being played, the role being played by F is X, and L here is being played by 4. So, because we can always write this as x cubed plus 4 cubed, right? So, the factorization of x cubed plus 64 will proceed using this formula with this for x for f and substituting 4 for L. So, we get quantity x plus 4 times, now we're going to square f, which is x, so x squared, minus FL, so we just multiply those, so we get 4x, plus L squared, which is 4 squared, which is 16. And that's it. We're done. And there's our factorization. Okay, simple. Just need to remember the formula, know how to apply it. Alright, so here it looks like we may have a difference of cubes. The GCF is 1. They have no other common factor. Now, if you memorize the tables that you were asked to memorize in one of the previous videos for cubes, you would recognize that 125 is indeed the cube of 5. So we can say that the first term here is the cube of 5u, and the second term is the cube of 6v. So we have quantity 5u cubed minus quantity 6v cubed. So that means if we're going to use f cubed minus l cubed formula, which is quantity f minus l times f squared plus fl plus l squared, that means we're going to use 5u instead of f, and we're going to use 6v for L. So the factorization is going to be basically 5u minus 6v, that's f minus L, times f squared, so the square of 5u, which is going to be 25u squared, plus the product of f and L, so just multiply these two, so we get 30uv, and then plus L squared, so plus, we're going to square 6v, so we get 6 squared v squared, so that's 36 v squared. And that should do it for that. There it is. If you don't get this at first, make sure that you then copy the problem, try it on your own, make sure you can do them on your own before you proceed. Go ahead and try this one before you come back to join me. Alright, so I hope you did realize we have a non-1 GCF, namely 5x squared, right? That's the greatest common factor of these two terms. So we go ahead and factor it out. That leaves us x cubed minus 8y cubed. So while we didn't have a sum or difference of cubes at first, after we factored out the GCF, as we know we always should, we do end up with a difference of 2 cubes. So we're going to be using again the f cubed minus L cubed. You notice how I write the formula every time I do one of these? That's exactly what I recommend that you do. You know what happens after you do that a few times? It's going to be totally memorized. Alright, so here the role of f is being played by x, and the role of L is being played by, you have to ask yourself, what do I have to cube to get 8y cubed? I think you'll know the answer is 2y, right? So we're going to plug into this formula with this for f and this for L. So the 5x squared you carry, and you're going to have times f minus L. So x minus 2y times f squared, which is going to be x squared, plus fl. So multiply these two, we get 2xy, and then plus L squared. So when you square 2y, we get 4y squared. And that's it. Now this second part of these factorizations, these are prime. There is no need to try to factor these. They're prime over the set of integers. They're factorable, but not with simple numbers. So we won't be dealing with those in this term. So you can, for our purposes, you can leave this part alone. Don't try to factor that because it won't. Alright, so here's our last problem. It's the bonus problem. I want you to think about this and see what you may actually do with it before you come back. Definitely try it. Alright, so I do hope you recognize the fact that we have ourselves a difference of squares here, right? So we should be able to use the f squared minus L squared formula, which is f plus L, quantity f plus L times quantity f minus L. So f, of course, here is being played by x plus y. L is being played by x minus y. So when we apply this formula with x plus y instead of f and x minus y instead of L, let's see what happens. So we get f, which is x plus y, plus L, which is x minus y. I didn't use parentheses because we're adding, and we normally don't need it when we're adding. The next one is going to be, now we're going to handle the f minus L part. So that's going to be x plus y minus quantity x minus y. Here we will need to use parentheses on the second part. So we're going to say minus quantity x minus y. So now notice that in the first group the y's cancel out, so you just get 2x, right? Now in the second group, let's go ahead and distribute that negative, so we get x plus y minus x plus y, right? Notice this time these x's will cancel out, so we end up with 2x times 2y, because y plus y is 2y. So finally we end up with 4xy. So we handle that very efficiently because we recognize the fact that we have to use the difference of squares formula. Now, had you not realized that, let me just show you, it would not be the end of the world. You could have used the f plus l squared formula to realize that you can get f squared plus 2fl plus l squared, and the f minus l squared formula to get f squared minus 2fl plus l squared. So the x plus y squared using this formula from our past would become x squared plus 2xy plus y squared minus, we're going to need parentheses after a minus. Now we're going to do x minus y squared, which is this formula. So we get x squared minus 2xy plus y squared. Now let's go ahead and distribute that negative in to see what happens. So we get minus x squared plus 2xy minus y squared. Notice that the y squares cancel out, the x squares cancel out. We only end up with 2xy plus 2xy, which is 4xy, which is of course the same thing we got doing it the other way. So either way is correct and fine. This is my recommendation. This is much simpler. You deal with much simpler expressions. So make sure that you can handle these in both methods for maximum benefit. It is always a great thing to be able to do the same problem in more than one way. That you start developing some real mathematical depth when you do that. So we learned quite a few different factoring techniques. Make sure you practice these through homework, and stay safe till our next video.